And now in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside this big triangle we have two circles and one square. The radius of the small circle is equal to 1 unit. The side length of the square is equal to 3 units, and our mission is to find out the radius of this big circle. So first of all, we'll define this vertex as A. We'll define the vertex here of the triangle as B, and we'll define the third vertex of the triangle as C. We'll define the center of the small circle as O. We define the center of the big circle as P. We define the point of tendency of tangent BC with this circle as Q. We define the point of tendency of tangent BC with this small circle as D. We define this point as point E. We define the touching point of the square with side BC of the triangle as F. We define the point of tendency of the side of the square with the circle as G. We define the touching point between side AC of the triangle and this square as H. We define the point of tendency of tangent AE with this circle as L. We define the point of tendency of tangent AC with this circle as K. And we define the point of tendency of side AC and the big circle as M. So here we join points L and O together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore LO is the radius of the circle that is equal to 1 unit. So here R equals to 1. So here we have the radius OL that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Note that all the angles inside the square are right angles, therefore this angle is equal to 90 degrees. This angle will be also equal to 90 degrees. This angle equals to 90 degrees, and finally this angle will be also equal to 90 degrees. And we also have here rule number 3. According to rule number 3, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here BC is one side of triangle ABC, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line BC at point F, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have on the upper side of BC at point F? We have this angle that is equal to 90 degrees. So this angle, the BC angle must be equal to 90 degrees also in order to complete the sum of the angles on the upper side of BC at point F to 180 degrees, this angle must be equal to 90 degrees. Likewise, if we focus on the upper side of BC at point E, this angle equals to 90 degrees, and for the same reason, the missing angle must be also equal to 90 degrees. Okay, here we have the radius of D that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We have inside quadrilateral OLED, we have 1, 2, 3 right angles. Again, inside quadrilateral OLED, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So inside quadrilateral LOED, we have 4 right angles. And any quadrilateral that has 4 right angles, here must be at least a rectangle if not a square. So we relate to quadrilateral LOED is a rectangle. So I write it down. Quadrilateral LOED is a rectangle. Why? Because it has 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, LO equals to ED. LO equals to ED. But LO equals to 1 unit. It is the radius of the small circle. So you can write here LO equals to 1. And from this equation, 1 equals to LO equals to ED. We will derive that ED is also equals to 1 unit. ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle LOED. So here I write it down that ED equals to 1 unit, according to what we have already found out. So likewise, according to the same rule, LE equals to OD. LE equals to OD. But we know that OD equals to 1 unit, it is the radius of the circle. So we can write down here that OD equals to 1, and from this equation, LE equals to OD equals to 1, we will derive that LE is also equals to 1 unit. Here LE equals to 1 unit. So we actually found out that quadrilateral LOED is not a rectangle but a square. Okay. So here, if we focus on side AG of this square, it is equal to 3 units. And side LE equals to 1 unit. So edge L equals to, here, edge L equals to edge E minus LE. Again, edge L equals to edge E minus LE. Edge E is 3 and LE is 1, so 3 minus 1 is 2. So in conclusion, we found out that edge L equals to 2 units. So here I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. So we actually can implement rule number 2 in our drawing, because in our drawing we have the common external point H, and from the common external point H, we have two tangents to this circle, tangent edge L and tangent edge K. And according to rule number 2, edge L equals to edge K. Edge L equals to edge K, but edge L equals to 2, therefore edge K must be equal also to 2. So we found out that HK equals to 2 units. Likewise, we'll focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CD and tangent CK. And according to rule number 2, they must be equal to each other. That is to say, CD is equal to CK. So, CD is equal to CK, so if we define CD as X, then CK must be also equal to X because of the fact that they are equal to each other. Okay? So, in the next step, we will implement the Pythagoras theorem on the right triangle AGC. On the right triangle AGC. According to the Pythagoras theorem, in the right triangle AGC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So the hypotenuse is HC, therefore the square of the hypotenuse is HC square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to HE square plus EC square. Repeat again, according to the Pythagoras theorem, on the right great triangle AGC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say HC square equals to AG square plus EC square. So here HC equals to 2 plus X, therefore HC square equals to 2 plus X square, and it is equal to edge E square. Edge E equals to 2 plus 1, that is 3, so edge E square is 3 squared, that is 9, plus EC square. Here EC equals to 1 plus X, or X plus 1. Okay, therefore EC square is X plus 1 square. So in conclusion, we found out that according to equation number 1, 2 plus X square equals to 9 plus X plus 1 square. Here we'll open the brackets on both sides of equation number 1, and we'll get that according to equation number 1, two plus X square equals to 2 squared, that is 4, plus X square plus 2 times 2x is plus 4x, and it is equal to 9 plus x plus 1 square. X plus 1 square equals to x square plus 1 square, that is 1, plus 2x. So here we have x square on both sides of the equation, so x square will get cancelled. what is left from this equation number 1? After we cancel the x squared, we have in this side of the equation 4 plus 4x, that is equal to 9 plus 1 is 10 plus 2x. So here we subtract 4 from this equation number 1, and we get that according to equation number 1, 4x is equal to 10 minus 4 is 6 plus 2x. So here we subtract 2x from this equation number 1, and we get that according to equation number 1, 4x minus 2x is 2x, that is equal to 6. Here we divide this equation number 1 by 2, and we get that according to equation number 1, x equals to 6 over 2, that is 3. So we found out that x equals to 3. So I write down in the drawing that x equals to 3. Here x equals to 3, and here also x equals to 3. In the next step, I will join points O and K together by a straight line. So point O is the center of the circle, point K is the point of the circle itself, therefore OK is the radius of the circle, that is equal to 1. Here the radius OK is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees also. So we join points C and O together by a straight line. So here we created two right triangles, triangle ODK and triangle OCK. So we prove that the two right triangles can go into each other according to side rule. So we prove that the right triangle OKC is congruent to the right green triangle ODC. So why those two right triangles can go into each other? First of all, KO equals to OD, they are both the radii of the circle, therefore they are equal to each other. KO equals to OD equals to 1. In addition, CK equals to CD, CK equals to CD, they are both equal to 3 units according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. CO equals to CO. It's a common side that belongs to both triangles. So you actually prove that the two green small right triangles can go into each other according to side rule. And so I write it down. I actually proved that the triangle KOC congruent to triangle ODC according to side rule. And from the fact that the two right triangles can go into each other, we conclude that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta. Why? Because they are equal to each other. Okay. In the next step, we'll join points D and K together by a straight line. By joining points D and K by a straight line, we created a triangle KDC. Actually, we conclude that CO is angle bisector of angle C. Angle bisector of angle C. It is already to see that the angle bisector CO bisects angle C into two halves, each half equals to theta. In triangle KDC. In triangle KDC. Okay, I'll repeat again. We actually found out that CO is angle bisector of angle C. It bisects angle C into two halves, theta and theta, in triangle KDC. Okay. In the next step, we'll join points P and M together by a straight line. Point P is the center of the circle. Point M is the point on the circle itself. Therefore, PM is the radius of the big circle that is equal to R. In the next step, we'll join points C and P together by a straight line. By joining points C and P together by a straight line, we created here two right triangles. Actually, we have here the radius PQ that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have the radius PM that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to the same rule number 1. So created, by joining points P and C together by a straight line, we created here two right big triangles, triangle MPC and triangle PQC. We prove that those two right triangles can go into each other according to side rule. So I'll write it down. We will prove that the right big triangle, triangle MPC, is congruent to the right big triangle, triangle PQC. So why those two right triangles can go into each other? First of all, PM equals to PQ, they are both the radii of the circle. PM is equal to PQ, that is the radius that we are looking for. They are both the radius of the circle, of the big circle. In addition, if we focus on the common external point C, from the common external point C, we have two tangents to the big circle. Tangent CM and tangent CQ. And according to rule number 2, they are equal to each other. So CM is equal to CQ according to rule number 2. And finally, PC is a common side that belongs to both triangles, so we can find out that PC equals to itself. PC equals to PC is a common side that belongs to both triangles. So we actually proved that the two big right triangles can point to each other according to side rule. So I write it down. We actually proved that triangle MPC can point to triangle PQC according to side rule. Okay? And for the fact that the two big triangles can point to each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two big triangles can point to each other, therefore the two corresponding angles must be equal to each other also. So if we define one angle as theta, then the other angle must be also equal to theta. Okay? So here we join points M and Q together by a straight line. Actually, from what we did here, we can conclude that CP is the angle bisector of angle C. Again, CP is the angle bisector of angle C. The second angle C. In triangle MQC, in the big triangle MQC. Okay, in triangle M. Okay, again, we can conclude that CP is the angle bisector of angle C, of angle C in triangle MQC. But we have already found out that OC is also angle bisector, or CO is also the angle bisector of the same angle, angle C. So we actually have two angle bisectors of angle C, CP and CO. Okay, so here we have a claim that CO passes through point P. Okay, our claim is that CO passes through point C. So I write it down. according to our claim, angle by sector CO passes through point P. I repeat again, our claim that is that angle by sector CO passes through point P. So we'll prove the claim in the negative way. So in the negative way, we will assume that angle by sector CO doesn't pass for point P. Okay, repeat again, in the negative way, we will assume that the angle by sector CO doesn't pass for point P. And we will arrive, due to the wrong assumption, we will arrive to a contradiction, and because of the contradiction, we will conclude that our assumption is not correct, and therefore angle by sector CO indeed passes for point P. So now, according to our assumption, we have here two angles. We have here angle DCO. I copy angle DCO. So we have here this is angle OCD, or can call it also angle DCO, it doesn't matter. And here angle DCO equals to theta, and you can see here from the drawing, from the original drawing, it is very easy to see that DC is part of side BC, or DC is part of the straight line BC. It is very easy to see. Here, this is part of the straight line BC, or in other words, you can say that DC and BC are located on the same straight line. Okay. can write here that DC leg DC and BC are located on the same straight line. Why? Because DC is part of BC. Now we'll also draw the second angle, this angle PCB. This angle is angle PCB. So we draw this angle PCB. So this is angle PCB that I draw, that I copied from the original drawing. So we found out that those two legs of the angle, they are both located on the same straight line. That is to say, leg DC and leg BC of the two angles, they are both located on the same straight line. And what about the second leg? Leg OC and leg PC. Here we have leg CO and leg CP, or leg OC and leg PC, it doesn't matter. So here, according to our assumption, CO doesn't pass for point P, therefore here CO doesn't located on the same straight line as CP. Here CO doesn't located on the same straight line as CP. Okay, according to our assumption that CO doesn't passes for point P, we'll conclude that CO doesn't located on the same straight line as CP. This is very clear from our assumption. Okay, that CO doesn't located on the same straight line as CP. Otherwise, here COP will be both on the same straight line, or point CP and O will be on the same straight line. But according to our assumption, CO doesn't pass for point P, therefore CO doesn't located on the same straight line as CP. So therefore, if we have here two angles, one leg of the two angles here are located on the same straight line, while the second leg of the two angles is not located on the same straight line. Therefore, those two angles can never be equal to each other. Why? Because in order that the two angles will be equal to each other, then if the first leg is located on the same side line, as you can see here, then the second leg must be also located on the same side line. But according to our assumption, it doesn't. Okay, therefore, you can conclude that those two angles are not equal to each other. So this angle is theta, then this angle must be equal to other angle than theta. That is to say, it will be equal to alpha, and alpha is not equal to theta. Okay? So in conclusion, we actually found out that angle C has two different angle bisectors. That is to say CO and CP that bisects it into two different halves, while the angle bisector CO bisects angle C into two halves that are theta and theta. The angle bisector CP bisects the same angle C into two different halves that each half equals to alpha and alpha. And this is a contradiction. Why? Because if for example the size of angle C is equal to 30 degrees, then any angle bisector of angle C will bisect it into two halves, that each half equals to 15 degrees and 15 degrees only, and not to any other halves. So you can write down that due to our assumption, we arrived to a contradiction, and therefore our assumption is not correct, and therefore we must conclude that the angle bisector CO passes for point P. Okay, so we finished with the proof. So we continue. We'll focus on triangle Again, right triangle, triangle ODC, this angle equals to theta. This angle equals to 90 degrees. Therefore, the phi of the angle, this angle, must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. This is the sum of the angles in any triangle. Likewise, we focus on the big right triangle, triangle PQC. On the big right triangle, triangle PQC, this angle equals to theta. This angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta, exactly for the same reason, that this angle equals to 90 degrees minus theta. In the next step, we will prove that the right big triangle, triangle PQC, this triangle is congruent to the small green triangle, triangle ODC. Okay, I write it down. So triangle, the right big triangle, triangle PQC is congruent. We prove that it is congruent to the right big triangle, triangle ODC. So why those two triangles can go into each other? First of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. Angle PQC, this angle is equal to this angle, that is actually also angle PQC, to angle DOC, I repeat again, angle PQC is equal to angle DOC, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other. Okay? So angle, this angle PQC angle PQC is equal to this angle, that is actually angle ODC, repeat again, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle, angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself as a common angle that belongs to both triangles. So we define angle theta as angle PCQ, and it is equal to itself, so we can define angle theta as angle OCD. Repeat again. Here, angle theta equal to itself. It's a common angle that belongs to both triangles. So we actually proved that the two right triangles can go into each other according to angle rules. So I write it down. We actually proved that triangle PQC, the big right triangle, is similar. This is the sign of similar to the right green small triangle, triangle ODC, according to angle similarity rule. Okay. And from the fact that the two right triangles can be similar to each other, we will derive that the following relationship exists between their sides. We will derive that PQ in the big right triangle over OD in the small right triangle is equal to QC in the big right triangle over DC in the small green right triangle. I'll repeat again. We will derive that PQ over CD equals to QC over DC. PQ over OD equals to QC over DC. Okay. PQ is the radius of the big circle that is equal to R. OD is the radius of the small circle that is equal to 1. And it is equal to QC. What is the value of QC? QC equals to 3 plus 1 plus 3, that is 7, plus QF. So we substitute QC by 7 plus QF. This is QF. Over DC. What is the value of DC? The value of DC, it is very easy to see that DC equals to X, that is equal to 3 units. So we substitute DC by 3. Okay, so here we found out that according to equation number 1, R equals to 7 plus QF over 3. Okay, so here we multiply this equation number 1 by 3, and we get that according to equation number 1, 3R is equal to QE plus 7. QE plus 7 here we subtract 7 from this equation number 1, and we get that according to equation number 1, QE is equal to 3R minus 7. QE is equal to 3R minus 7, so we write down in the drawing that QE equals to 3R minus 7. QE is equal to 3R minus 7. So because of the fact that the side length of the square is equal to 3 units, we will examine 3 cases for the value of the radius that we are looking for, the radius of the big circle. The first case that we will examine is, we will examine if the radius of this big circle is less than 3 units. We'll examine the second case, that if the radius of this circle is equal to 3 units, and finally we'll examine the third case, that the radius of this circle is greater than 3 units. So, in the first case, we'll assume that the radius of this big circle is less than 3 units. So if R is less than 3 units, therefore we will have a circle with a radius that is less than 3 units. Okay? So, if the radius is less than 3 units, it means that the square that is 3 units, it will be longer than the radius. So here, the side length of the square is equal to 3 units. Therefore, it will be longer than the radius. Here, this is the radius R, and this will be also the radius R. And we actually know that the square is tangent to the circle. Therefore, according to rule number 1, this angle will be equal to 90 degrees. So actually here we have P. So here in quadrilateral inside quadrilateral PGQF, in this quadrilateral we have 1, 2, 3 right angles. Again, inside quadrilateral PGQF we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay, the fourth angle equals to 90 degrees. Therefore, inside quadrilateral PGQF we have 4 right angles. Therefore, we will relate to quadrilateral PGQF as a rectangle because it has 4 right angles. Quadrilateral PGQF is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. Therefore, in rectangle PGQF, PQ must be equal to GF. PQ must be equal to GF. But we know that PQ is the radius of the circle, so we can write that PQ equals to R. And from this equation R equals to PQ equals to GF, we will derive that GF is also equals to R. So here GF is equals to R. Okay. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that PG, here PG is equals to QF. PG is equals to QF, but here PG is the radius of the circle that is equal to R, so I can write here that PG equals to R, and from this equation R equals to PG equals to QF, we will derive that QF is also equals to R. QF is equals to R. And right here that QF equals to R. But here we found out that QF equals to R. But we also know that QF equals to 3R minus 7. Okay, so here from one side QF equals to R, from the other side QF equals to 3R minus 7, therefore we can write down that R equals to 3R minus 7. Here we subtract R from this equation and we will get that 3R minus R is 2R, so 2R minus 7 equals to 0. We will add 7 to this equation and we will get that 2R equals to 7. We will divide this equation by 2 and we will get that R equals to 7 over 2, that is 3.5 units. So according to our assumption, R is less than 3 units. But here we found out that R equals to 3.5 units. R cannot be simultaneously be equal to 3.5 units and also be less than 3 units. So due to the contradiction here, we conclude that R cannot be less than 3 units. Okay? R cannot be less than 3 units. Okay? In the next step, we will examine the second case, that R equals to 3 units. Okay, so if R equals to 3 units, then we will have a circle. We will have a circle with a radius of 3 units. So I will draw the circle with a radius of 3 units. So here, case number 2. If R equals to 3 units, this is case number 2. So here we know that the radius of this circle R is equal to 3 units. And we also know that the side length of the square is equal to 3 units. So here R equals to 3. This again of course equals to 90 degrees according to rule number 1. Those two angles are also equal to 90 degrees. So here we have we have inside quadrilateral PGQF, this quadrilateral, we have 1, 2, 3 right angles, 1, 2, 3 right angles, here 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral PGQF we have 4 right angles. Therefore quadrilateral PGQF is a rectangle because it has 4 right angles. And the opposite sides of the rectangle are equal to each other. That is to say, PG is equal to QF. PG is equal to QF. But PG equals to R, that is equal to 3 units. So we can write here that PG equals to 3. And from this equation 3 equals to PG equals to QF, we conclude that QF is also equals to 3 units. So from one side QF equals to 3 units. From the other side we have already found out that QF equals to 3R minus 7. So we can write here that QF equals to 3R minus 7. Also, and from this equation 3R minus 7 equals to QF equals to 3, we will derive that 3R minus 7 is equals to 3. Here we'll add 7 to this equation and we'll get that 3R is equal to 3 plus 7 is 10. So we'll divide this equation by 3 and we'll get that according to this equation R equals to 3 and a third. According to our assumption, R equals to 3 units. But here we get that R equals to 3 and a third. So R cannot equal both to 3 and a third and 3. So it is a contradiction. Therefore, we'll cancel case number 2. That is to say, R cannot be equal to 3 units due to the contradiction that we got here. Okay? So, only the third case is left, that R is greater than 3 units. Case, according to case number 3, we have R that is greater than 3 units. So if R is greater than 3 units, then the radius of the circle that is greater than 3 units will be longer than the side length of the circle that is equal to 3 units. So we'll draw accordingly the drawings of the circle and the square. So here, the side length of the square will be shorter than the radius. Okay, so I draw it accordingly. So I have here So here from point L we draw perpendicular on the radius PQ. Repeat again, from point L we draw perpendicular on the radius PQ. So here this angle is equal to 90 degrees and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point L and the radius PQ as T. So here this angle equals to 90 degrees, this angle also equals to 90 degrees according to what we have already found out. And this angle equals to 90 degrees according to our construction. So inside quadrilateral TLQF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Okay? So quadrilateral TLQF has 4 right angles, therefore quadrilateral TLQF is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, here QF equals to 3R minus 7. That is to say, TL, side TL of rectangle TLQF equals to QF. TL equals to QF. But according to what we have only found out, that QF equals to 3R minus 7. So from this equation TL equals to QF equals to 3R minus 7, we will derive that TL is also equals to 3R minus 7. TL is equals to 3R minus 7. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that LF is equal to TQ. LF is equal to TQ. But here LF is the side length of the square that is equal to 3 units. So from this equation LF equals to TQ equals to 3, we'll get that LF is also equals to 3 units. We'll get that it's actually, we have LF that is equal to TQ. So here we know that LF is equal to 3 units, and from this equation 3 equals to LF equals to TQ, we will derive that TQ is also equals to 3 units. So here TQ equals to 3 units. And what is the value of PT? Here it is very easy to see from the drawing that PT is equal to PQ minus TQ. PT equals to PQ, PT equals to PQ minus TQ, so PT is equal to PQ, that is R, minus TQ, that is 3. So in conclusion, found out that PT is equals to R minus 3. In the next step, we will join points P and L together by a straight line. So here, point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that is equal to R. So in the next step, I will copy the right green triangle PTL in a new page, and we will implement the Pythagoras theorem on the right green small triangle PTL. pt equals to r minus 3, dl equals to 3r minus 7, and the hypotenuse PL equals to R. So this is the right triangle PTL that I copied from the original drawing. We'll implement the Pythagoras theorem on the right triangle PTL. So here, by PT is a relation from Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is PL, therefore the square of the hypotenuse is PL square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PT square plus TL square. So here PL equals to R, therefore PL square is equal to R square, and it is equal to PT square. PT equals to R minus 3, so PT square will be equal to R minus 3 square plus TL square. TL equals to 3R minus 7, therefore TL square will be equal to 3R minus 7 square. So here we'll open the brackets on this side of equation number 1, and we'll get that according to equation number 1, R square is equal to R minus 3 square. R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3R minus 7 square. 3R minus 7 square equals to 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3 is minus 6, and minus 6 times 7 is minus 42. So in total, the expression will be equal to minus 42R. So here we have R square on both sides of equation number 1, so R square will get cancelled. So what is left from equation number 1 after we cancelled R square? In this side of the equation we have 0, that is equals to 9 plus 49 is 58, plus 9R square, minus 6R minus 42R is minus 48R. So we have here a quadratic equation. According to this quadratic equation, 9R square minus 48R plus 58 is equal to 0. So here we have the general formula for a quadratic equation, that ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a is equal to 9, the coefficient b is equal to minus 48, and the coefficient c is equal to 58. And the variable that we are looking for is r, so x equals to r, x equals to r. So here we'll get that r equals to minus b, b equals to minus 48, so therefore minus b is minus 48, that is plus 48, plus minus square root of b squared. So b squared is minus 48 squared, that is 2304, minus 4 times a is 9, so minus 4 times 9 is 36, minus 46, and minus 46 times 58 is 2000 88 over 2a. A is 9, so 2a is 18. So here we found out that R equals to 48 plus minus 2300. 4 minus 2088 is 2016 over 18. So R equals to 48 plus minus the square root of 216 is 14.6969 over 2a over 18. So here we found out that we have two solutions for R. The first solution for R is that R equals to 48 minus 14.6969 over 18. So here R equals to 48 minus 14.6969 is 33.3031 over 18. That is equal to 1.85. So here we found out that R equals to 1.85, but we have only found out that R cannot be less than 3 units, and 1.85 is less than 3 units. Therefore we cancel this solution and we left only with the second solution, that R equals to 48 plus 14.6969 over 18. That is actually equals to 62.6969 over 18. That is equal to 3.483 units. So the radius of this big circle is equal to 3.483 units. We finished the question. In the next step, I'll summarize the lecture. So, in the drawing, we have a big triangle. Inside the big triangle, we have two circles and a square. The radius of the small circle is equal to 1 unit, and the radius and the side length of the square is equal to 3 units, and our mission is to find out the radius of the big circle. Okay, so actually I presented to you 3 rules that we use them all over the question. So I'll present again the 3 rules that we used in order to solve the question. Okay. We have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have here tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. So whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. And finally, we have rule number 3. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So here CD is a straight line. So if you focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have on the upper side of CD at point O? We have here angle alpha and angle theta. And according to this rule number 3, alpha plus beta must be equal to 180 degrees. So we use these 3 rules, and using the 3 rules we got here this drawing. We actually, by using the 3 rules, we actually concluded that quadrilateral LO, the small quadrilateral LOED, is a rectangle. It has 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrilateral LOED is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, LO is equal to ED. LO is equal to ED. Here, but we know that LO equals to 1 unit. It is the radius of the circle. So for this equation, 1 equals to LO equals to ED, we derive that ED is also equals to 1 unit. Here, ED is also equals to 1 unit. Likewise, according to the sum rule, we have here LE is equal to OD. LE is equal to OD, but OD is the radius of the circle that is equal to 1. So from this equation, L equals to OD equals to 1, we derive that LE is also equals to 1. LE equals to 1, so actually found out that quadrilateral LOED is not a rectangle, but a square, because all of its sides are equal to each other. Then we actually used also rule number 2. If we focus on the common external point, point H, from the common external point, point H, we have 2 tangents to the circle, tangent HK and tangent edge L. And according to rule number 2, they are equal to each other. What is the length of LH? LH equals to 3 minus 1, that is 2. So we know that LH equals to HK, and L is equal to 2 units. Therefore, HK will be also equal to 2. Likewise, according to the same rule, if you focus on the common external point, point C, from the common external point, point C, we have 2 tangents to this circle, tangent CD and tangent CK, and according to rule number 2, they are equal to each other. That is to say, CK equals to CD. So if we define CK as X, then CD will be also equal to X, because they are equal to each other. Then we implemented the Pythagoras theorem on the right green triangle, edge EC. The right green triangle, edge EC. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, HC square equals to HG square plus AC square. I'll repeat again, HC square equals to HG square plus EC square. Here, HC, the hypotenuse HC equals to 2 plus X. Therefore, HC square is equal to 2 plus X square. Side LE equals to side edge E equals to 3. Therefore, AG square is 3 squared, that is 9, plus EC square. EC equals to 1 plus X, therefore EC square will be equal to 1 plus X square, or X plus 1 square. So in conclusion, we found out that according to equation number 1, 2 plus X square equals to 9 plus X plus 1 square. Here we open the brackets on both sides of this equation number 1, and we found out that 2 plus X square equals to 2 square, that is 4, plus X square, plus 2 times 2x is 4x, that is equal to 9, plus x plus 1 square. x plus 1 squared equals to x squared plus 1 plus 2x. Here we have x squared both sides of the equation, so x squared will get cancelled. And what is left from equation number 1 after we cancel x squared? In this side of the equation we have 4 plus 4x. In the other side of the equation number 1 we have 9. We have 9 plus 1 is 10. So we have 10 plus 2x. So here we subtracted 4 from this equation, equation number 1, and we found out that 4x equals to 10 minus 4 is 6 plus 2x. So here we divided this equation, equation number 1 by 2, and we got that we subtracted 2x from this equation, equation number 1, and we found out that 4x minus 2x is 2x, so 2x equals to 6. We divided this equation, equation number 1 by 2, and we found out that x equals to 6 over 2, that is 3. Okay. Then we joined points K and O together by a straight line. We joined points C and O by a straight line. And we proved that the two green right triangles can go into each other according to side rule. So why those two triangles can go into each other? First of all, KO equals to OD equals to R, they are both the radii of the circle, therefore they are equal to each other. In addition, we know that CK equals to CD, they are both equals to 3 units according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. So we actually proved that the two green small right triangles can go into each other according to side rule. And from the fact that the two right green triangles can go into each other, we derive that those two angles are equal to each other. According to the rule that corresponding angles that can go in triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta, because they are equal to each other. Then we joined points K and D together and created triangle KDC. So we can conclude from what we did until now that CO is the angle bisector of angle C in triangle KDC. I'll repeat again. Here, CO is the angle bisector of angle C in triangle KDC. Why? Because it bisects CO bisects angle C into two equal angles, theta and theta. Therefore, CO is the angle bisector of angle C. Then we join points P and M together by a straight line. Point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of the circle, that is R. Then we proved that those two triangles can go into each other according to side rule. I will explain what I mean. Here PM equals to PQ, because they are both the radii of the circle, therefore they are equal to each other. In addition, if we focus on the common standpoint point C, from the common standpoint point C we have two tangents to the big circle, tangent CM and tangent CQ. And according to rule number 2, they are equal to each other, so CM equals to CQ. And finally, CP is a common side that belongs to both triangles, so CP equals to itself. So we found out that those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in can go into triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be equal to each other. So if one angle is theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Then we joined points M and Q together and created triangle MQC. So we can conclude from what we did until now that PC is also the angle bisector of angle C because it bisects angle C into two halves, theta and theta, in triangle QMC. Okay, so I repeat again. CP is the angle bisector of angle C in triangle MQC. And we have already found out that CD is also the angle bisector of angle C. So actually, angle C S2 angle bisector CP and CO. Okay, and then we have a claim here that CO, the angle bisector CO passes for point P. Repeat again. CO, the angle bisector CO passes for point P. We actually proved this claim in the negative way. That is to say, we assumed that CO doesn't pass for point P, and from that assumption, we arrived to a contradiction. Therefore, we concluded that our assumption is not true. Therefore, we must conclude that CO passes for point P. Okay? So, our assumption is that CO doesn't pass for point P. Here, CO doesn't pass for point P. So, according to our assumption, we have here two angles. Angle DC OCD, or angle, we have here angle OCD that is equal to theta, and it is very easy to see that here CD is part of BC. CD is part of BC. Therefore, you can say that CD and BC, they are both located on the same straight line. Okay, here CD and BC, they are both located on the same straight line. And then we draw the second angle, that is angle PCB. Angle PCB. This is angle PCB that we draw. So here, in both angles, one leg is located on the same straight line. That is to say, CD and BC, they are both located on the same straight line. So those two angles have one leg that is located on the same straight line. What about the second leg? The second leg is leg PC and leg OC. What about the second leg? Here we have a leg CO and leg CP. According to our assumption, CO doesn't pass for point P. If CO doesn't pass for point P, it means that CO is not located on the same straight line as CP. Otherwise, CO must be located on the same straight line as CP. But according to our assumption, CO doesn't pass for point P. Therefore, CO is not located on the same straight line as CP. So if CO doesn't located on the same straight line as CP, it means that the second leg is not located on the same straight line in both angles. Okay? CO doesn't located on the same straight line as CP. And in order that those two angles may be equal to each other, if one leg is located on the same straight line, then the other leg must be also located on the same straight line. But it doesn't. It doesn't because according to our assumption, CO doesn't pass for point P. Therefore, CO is not located on the same straight line as CP. Therefore, those two angles must be different angles. If this angle is theta, then this angle must be equal to angle alpha, and theta is not equal to alpha. Okay? So here we actually concluded that angle C is two different angle bisectors that are CO and CP that bisect it in two different halves. While the angle bisector CO bisect angle C into two halves that are theta and theta, angle bisector CP bisects angle C into two other halves that are equal to alpha and alpha. And this is a contradiction. Why? Because if angle C is equal to 30 degrees, then any bisector that bisects angle C will bisect this into two halves, that is 15 degrees and 15 degrees, and not any other halves. Okay? So, due to the contradiction, we will conclude that our assumption is not correct, is not true. Due to the assumption, we arrived to a contradiction. The contradiction is that angle C has been bisected by two angle bisectors that bisect it into two different halves. That is impossible. And therefore, our assumption that OC doesn't pass for point P is not correct. So we will conclude that CO passes for point P. Okay? Therefore, CO must pass for point P. Otherwise, we get to a contradiction. Okay? So, in the next step, we focus on triangle, again, triangle ODC. This angle equals to theta, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on triangle PQC, the big triangle. This angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. Then we proved that those two right triangles are similar to each other according to angle similarity rule. So, why triangle PQC is similar to triangle ODC? Because first of all, those two angles are equal to each other. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Then, in addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta, is a common angle that belongs to both triangles, so this angle equals to itself. So we actually proved that those two triangles are similar to each other according to side rule. Okay? And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PQ in the big triangle over OD in the small triangle is equal to QC over DC. Is equal to QC over DC. I repeat again. We conclude that PQ over OD equals to QC over DC. Here PQ is equal to R. OD is equal to R, it is equals to 1, it is the radius of the small circle. QC, what is the value of QC? QC is equals to 3 plus 1 plus 3 plus QF. So in total, QC equals to 7 plus QF. So substitute QC by 7 plus QF. DC equals to X, that is equal to 3 units. So substitute DC by 3. And we got that R equals to 7 plus QE over 3. We multiply this equation number 1 by 3, and we found out that 3R equals to QE plus 7. We subtracted 7 from this equation, and we found out that QE equals to 3R minus 7. Here QE is equals to 3R minus 7. Then because of the fact that the side length of the square is equal to 3 units, we examined 3 cases for the value of the radius of this big circle. Either the radius of this big circle could be less than 3 units, it could be equal to 3 units, or it will be greater than 3 units. We examined each case in order to find out the value of the radius. In the first case, if r is less than 3 units, so we'll get this drawing. In this drawing, here the side length of the square is 3 and the radius is less than 3 units, so the side length is longer than the radius. So you can see here. So in this quadrangle PGQC, we have 1, 2, or 3 right angles. This again equals to 90 degrees according to rule number 1. So in quadrangle PGQC, we have 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore in quadrangle PGQC, we have 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PG is equal to QF. But PG is equal to QF. But PG, yeah, but PG is equal to R. Okay, therefore QF must be also equal to R. Likewise, according to the same rule, PQ equals to GF. PQ equals to GF, but PQ equals to R, it is the radius of the circle, so can I derive PQ equals to R? From this equation, R equals to PQ equals to GF, we will derive that GF is also equals to R. So here, actually found out that quadrangle PGQF is a square because all of its sides are equal to R. So from one side QF equals to R. From the other side we will find out that QF equals to 3R minus 7. Therefore QF is equal to R, that is equal also, and it is also equals to 3R minus 7. Therefore R equals to 3R minus 7. Here we subtracted R from this equation and found out that 3R minus R is 2R, R minus R is 0, so we got here 2R minus 7 equals to 0. We added 7 to this equation and found out that 2R equals to 7. Here we divided this equation by 2 and found out that R equals to 3.5 units. According to our assumption, R is less than 3 units, but here we got that R equals to 3.5 units. R cannot be both. R cannot be equal to both to 3.5 units and will be less than 3 units. Therefore, we have a contradiction. Therefore, R cannot be less than 3 units due to the contradiction. Then we examined the second case, that R is equal to 3 units exactly. So if R equals to 3 units, here we will have this drawing. R is 3, so this is 3, 3, and the square, the side length is also 3, so this is 3 also. And we know that QF equals to 3R minus 7. So here, inside quadrangle PGQF, we have 1, 2, 3 right angles. This angle equals to 90 degrees according to rule number 1. So if we have 3 right angles, the fourth angle must be also equal to 90 degrees. So quadrangle PGQF is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say PG equals to QF. PG equals to QF, but we already found out that PG equals to 3 units. So from this equation, 3 equals to PG equals to QF, we will derive that QF is also equals to 3 units. So from one side QF equals to 3, and from the other side QF equals to 3R minus 7. So from this equation we will derive that 3r minus 7 equals to 3. We added 7 to this equation and we found out that 3r equals to 10. We divided this equation by 3 and we found out that the radius of this circle equals to 10 over 3, that is 3 and a third. But according to our assumption, r equals to 3. R cannot be both equals to 3 and to 3 and a third. So due to the contradiction, we cancelled this possibility. R cannot be equal to 3 units. So we left only the third possibility with the third case, that the radius of this circle is greater than 3 units. So if the radius of this circle is greater than 3 units, then the radius here will be longer than the side length of the square, that is 3 units. So here inside quadrangle, so from point L we do perpendicular on the radius PQ. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So here we have 1, 2, 3 rectangles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrangle TLQF is a rectangle. Why? Because it has 4 rectangles. And we know that the opposite sides of a rectangle are equal to each other. That is to say TL is equal to QF. Okay, but QF equals to 3r minus 7. So from this equation TL equals to QF equals to 3r minus 7, we will derive that TL is also equals to 3r minus 7. Likewise, we also know that according to the same rule, TQ is equal to LF. Here TQ equals to LF. But here LF equals to 3, and from this equation 3 equals to LF equals to TQ, we will derive that TQ is also equals to 3 units. Okay, and what is the value of PT? PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. So PT equals to PQ, that is R, minus TQ, that is 3. So in conclusion, we found out that PT equals to R minus 3. As we already found out that TL equals to 3r minus 7, we join points P and L together by a straight line. Point P is the center of the circle. Point L is the point of the circle itself. Therefore PL is the radius of this circle, that is equal to R. Okay, then we implemented the Pythagoras theorem on the right green triangle, triangle PTL. I copied the right green triangle, triangle PTL in this new page and we implemented the Pythagoras theorem in this right triangle, triangle PTL. According to the Pythagoras theorem in the right green triangle, triangle PTL, the square of the equators equals to the sum of the squares of the perpendiculars. That is to say, PL square equals to PT square plus TL square. PL square equals to PT square plus TL square. PL is R, so PL square is R square. PT is R minus 3, therefore PT square is R minus 3 square. Plus TL square. TL is 3r minus 7, therefore TL square is 3r minus 7 square. We open the brackets on both sides, on this side of the equation, and we found out that r square equals to r minus 3 square. R minus 3 square is r square plus 3 square plus minus 2 times r times 3, that is minus 6r, plus 3 minus r square. 3r minus 7 square is equals to 3r square, that is 9r square, plus 7 square, that is 49. Minus 2 times 3 is minus 6, and minus 6 times 7 is minus 42. And so this expression will be equal in total to minus 42r. Here we have r square on both sides of the equation, so r square will get cancelled. So we left only with 0, that is equal to 9 plus 49, that is 58. Minus 6r minus 42r is minus 48r, plus 9r square. So here we have the quadratic equation that 9r square plus 48r plus 58 equals to 0. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, c are the coefficients, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58, and the variable that we are looking for in our specific quadratic equation is r, so x equals to r. We put the data inside the equation for x and found out that r, x equals to r, so here r equals to minus b, b equals to minus 48, so minus b is minus 48, that is plus 48, equals to b square, equals to the square root of b square. B is minus 48, therefore b square is minus 48 squared, that is 2300, so 4. Minus 4 times a is 9, so minus 4 times 9 is minus 36, times c is 58, so minus 36 times 58 is minus 2088. All divided by 2a. A is 9, so 2a is 18. So in conclusion, found out that 2304 minus 2088 is 2016. So inside the root we left only 2016. So we got that r equals to 48 plus minus square root of 216 over 18. The square root of 216 is 14.6969. So here we have two solutions that are possible for r. The first solution for r is that r equals to 48 minus 14.6969, that is equal to 33.3031 divided by 18 is 1.85. But because of the fact that we have already found out that the radius of the big circle cannot be less than 3 units, and 1.85 is less than 3 units. Therefore, this solution is not correct solution. We cancel the solution, and we left only with the second solution, that r equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969, and if we divide it by 18, we get that r equals to 3.483 units. So we found out that the radius of this big circle is equals to 3.483 units, and that is greater than 3 units. Therefore, according to our analysis, the radius of this circle can be greater than 3 units. Therefore, the answer to the question is that the radius of this big circle is equal to 3.483 units. Okay, thank you very much.